Here's section 12.3, where we're going to analyze energy in simple harmonic motion. Our goals here are to explain how energy converts from one form to another in a simple harmonic oscillator, and also to use these energy considerations to solve some oscillation problems. Now, we've already looked at simple harmonic motion in terms of forces, but here we want to see what we can do with energy. So what has to be true in order to conserve energy? Well, specifically, if you want to conserve mechanical energy, your system would have to be isolated. That means that if we were to put our block spring system on a frictionless surface, then our mechanical energy would in fact be conserved. Even further, if the spring was considered massless, the m that we're talking about in these energy equations would just apply to the mass of the block. This would make things a little bit easier and simplify things a bit as we work through our energy problems. So we'll assume this unless we're told otherwise. Now, how do you actually find the kinetic energy for the block spring system in simple harmonic motion? Well, of course, kinetic energy is equal to 1/2 mv squared. But what we also need to remember is that in the last section, we found an expression for the velocity in simple harmonic motion, and it was equal to negative omega a times the sine of omega t plus phi. So if we put that in for v and square it, that's where we're getting this expression that you see here. We have the 1/2 m, and then we have that v value that we had here squared. For potential energy in a simple harmonic oscillator, we know that the potential energy for an oscillator is equal to 1/2 kx squared. Again, that just came from the potential energy of a spring moving back and forth. Now, because for an oscillator we have the equation for position x equal to a cosine of omega t plus phi, we can come to this equation, and where we see the x squared, we'll square this value here and plug that in. So that's where we get the 1/2 k a squared cosine squared of omega t plus phi. So if we wanted to look at the total mechanical energy, we would have to add our kinetic plus our potential. So we've got our kinetic expression here plus our potential expression here. You can see that this is starting to look really, really messy if we want to have an equation for total energy. But hang on for just a minute and you're going to see what happens. Now, we know that omega squared is equal to k over m. So over here, we could actually rewrite this as k over m. These m's would cancel out. And what we find is that the kinetic energy expression has a 1/2, a k, and an a squared. And so does the potential energy expression. So we could pull all of that outside and leave the rest. And notice that the rest leaves you with a sine squared plus a cosine squared. Well, sine squared plus cosine squared is just equal to 1. So ultimately, we get this really nice simplified expression for total energy to be equal to 1/2 k a squared. Now we can see that the total energy is actually a constant that is proportional to the square of the amplitude, which makes sense because if we were to look at this block on a spring, and maybe this is the equilibrium position here, but then we were to stretch that spring further and that block further and pull it out to some amplitude out here. At that maximum amplitude, all of the energy would be stored in potential energy. So it makes sense that our total energy could be written as all of that energy stored in potential at the maximum amplitude. Now note that the total energy here could be then set to the kinetic energy at the equilibrium position. So although all of the energy is in potential out here, once the thing turns around and begins moving back through the equilibrium position, at equilibrium, none of the energy would be in potential anymore since it's at the equilibrium and the spring is not stretched, but everything would be in kinetic. So we could actually set our total energy equal to kinetic energy if we were at the equilibrium position. Now again, this all works for the simplification model of a massless spring. If the spring had some sort of mass, some of that kinetic energy would have to be associated with the motion of the spring itself. So we will assume massless springs unless we're told otherwise. Now, a place where you can kind of study this motion, really you get this back and forth motion of the spring being pulled out to our maximum amplitude and having everything in potential. But then it comes back through when you release it, comes through, turns into kinetic here, continues to move, turns back into potential here where the spring is compressed, and then you just get this back and forth oscillation, right? It comes back through here, turning back into kinetic, and stretching again out here, turning back into potential. And you see this back and forth oscillation. If you were to look on page 383 in your books, you'll see a nice graph and table that's set up for you there that really compares this motion and looks at position, velocity, acceleration, and the energies at all these different places along the oscillator's motion. You can study that, and we will come back to it and talk about it more in class. Now, because the conservation of energy law allows us to set our total energy expression equal to our kinetic plus our potential at any point, we could solve for the velocity at any point. So we know that if we were to simplify this, we would get an expression that looks like this. Remember, square root of k over m is really just equal to omega squared. And we get then this expression of plus or minus omega squared times the square root of a squared minus x squared. This gives you the velocity at any point along the motion. It is a plus or a minus because notice that the block could be moving this way through any point along its motion, or it could be oscillating back the opposite way. And again, this could be at any point along that motion, but it would give that positive or that negative velocity. Now let's try our hand at actually using some of these equations. Here we have a half-kilogram object that's connected to a massless spring with a force constant of 20 newtons per meter. It's going to oscillate on this horizontal frictionless track. We want to calculate a few things. To start, we want to calculate the total energy of the system and its maximum velocity if it has an amplitude of 3 centimeters in its motion. Now, to find the total energy, remember, total energy can simply be found with a 1/2 Ka squared. So in this problem, we said that the K of the spring was 20 newtons per meter, and we said the maximum amplitude of the motion was 3 centimeters, or 0.03. Go ahead, plug that into your calculators. You'd find that you get a maximum energy of 0.009, and that would be measured in joules. Pretty simple to use, right? Now, to find the maximum velocity of this thing, we could set this total energy equal to the kinetic energy, or 1/2 mv squared. When you solve for the v here, again, go ahead, plug it into your calculators. When you solve for that v, you would get a plus or minus 0.19 meters per second. We do put the plus or minus on there because, again, it could go through that equilibrium position in either direction, coming this way or coming back this way. And again, it is at the equilibrium position where our velocity is going to be maximized. Let's look at some of the other questions. Next, they ask, what is the velocity when the object is at a position of 2 centimeters? Here, we could go back to the equation that I showed you on the last slide. That equation said that v is equal to plus or minus the square root of k over m times the quantity a squared minus x squared. When we plug in our values, our k was 20, our mass is 0.5, the maximum amplitude was 0.03, and we are looking at an x position of 0.02. So, make sure that you square each of those position values. Plug all of this stuff in. Go ahead and pause the video if you need to. You would find that your velocity at that point is equal to a plus or minus 0.141 meters per second. Now last, we ask about energies. What is the kinetic energy at this 2 centimeter location? and what is the potential energy at the 2 centimeter location. For the kinetic energy, we know that that is equal to just a 1/2 mv squared. So we can plug in our 1/2, the mass of the object, and we just found the velocity at that position of 2 centimeters. So we can plug in the value we found and square it. And we'd find that our kinetic energy at this location is equal to about 0.005 joules. To find the potential energy at this location, we know that potential energy is equal to a 1/2 kx squared. So 1/2 times k times the x position of 0.02 squared leaves us with a potential energy of 0.004 joules. Now notice that when we look at this given location, it's not all the way out to the maximum amplitude, but it's somewhere out a little shorter than that, so it hasn't quite reached that position and still has both a little kinetic and potential at this location. That when we look at the kinetic energy at that spot and the potential energy at that spot, that these two values add up to our total energy, which of course makes sense that at any point our total energy would be conserved in this isolated system. When we come back to class, we'll try some more problems together.